There's a second algebra technique you can use to find the intersection point between two lines. It's a bit abstract to try and explain why it works, which is why the substitution method is a little easier to start with. For this one, you just have to look at these two equations and see that there are some y's and some x's in that one. There are some y's and some x's in that one. And if I could balance the number of y's or the number of x's in these equations, I should be able to subtract one equation from the other in order to eliminate that variable. So this one, for example, I have y equals 5 minus 4x. I'm going to take that and I'm going to just write it underneath of this one. Now, if you look at this equation and this equation, there's exactly one y here, and there's exactly one y here. So if I were to subtract those two equations, subtract these from each other, a y minus a y is nothing. Doesn't matter what value the y is, because the y's have to match at the point of intersection. This thing and this thing are the same, and the thing subtract itself is always nothing. Now if you look at the other side, I have a 7 subtract a 5. Well, that leaves me with 2. And then here, this is where it's a little tricky because of the negatives. If I take negative 3x and I subtract negative 4x, double negatives act like positives. Negative 3x plus 4x would be 1x. So this minus this gives me 1x. So to finish, kick this 2 across. And technically divide by 1, but you don't really need to divide by 1 because it doesn't change the answer. I have my x value there at negative 2. So once you have an x value, you can just take it and pop it into either this y or this y. I'll just use that one. So negative 4 times negative 2 is plus 8, and 5 plus 8 is 13. So my point of intersection then for these two lines is negative 2 on the x, 13 on the y. Now that was kind of clean when there were no fractions involved, so I'm just going to clear this off and we'll try one that has fractions. All right, so I'm going to take this one and write it underneath this one because it's a little easier to subtract that way. 11 over 3 minus plus 2/3 of x. Okay. Now I could do y minus y and get 0, and then that would be eliminated. But then I'm going to have to multiply, or I'm going to have to subtract 8/5 from 11/3, and I don't want to do that with fractions. So I'm going to scale both of these equations up to eliminate the fractions. So this one, to get rid of divide by 5, I'm going to have to multiply by 5. So if I do that, 5 of these is then 8 minus 7x. Now if I do the same thing to this one, to get rid of 3's in the denominator, I have to multiply by 3. So 3 times y would be 3y's. Then I'd have 11 plus 2x. So I've eliminated the fractions, which is excellent, smiley face for that. But I've created a new problem in doing that. I don't have matching y's anymore, right? If I did 5y minus 3y, I would get 2y, and that would not have eliminated the y. So I'm going to have to scale these things up again to try and get these to match. And if you think about it, if I took this line and tripled it, that would put 15 here. If I took this line and multiplied it by 5, that would put 15 here. And then I'd have a match. So I'm going to do that. 5 times 3 is 15y equals 3 times 8 is 24. 3 times negative 7 is negative 21. If I multiply this equation by 5, 5 times 3 is 15. 5 times 11 is 55. 5 times 2 is 10. So now, if I do this equation, subtract this equation, I will end up with a 0. Because 15 and 15 match each other perfectly. Carrying through, 24 minus 55, that's negative 31. And negative 21 minus 10 would be negative 31 as well. So I want this to say x equals a number. So I'm going to take this and I'm going to get it over there by adding 31 to both sides, 31x. This gives me 31x equals negative 31. And I just need to divide out this 31. So x equals negative 1. Yep. But once I have an x value, I just need to pop it in for y. So I've got the y value here. Two-thirds times negative 1 would be subtract 2/3. 11/3 minus 2/3 is 9/3, which gives me 3 as my final answer. So I have a point of intersection at x equals, disregard, negative 1, 3. I have an example here where the lines are in ax plus by equals c format. And we sort of skipped over that format because it was difficult to sketch, but when you're doing intersections, this format is really easy because there are never any fractions and you never have to do any of that scaling up to deal with the fraction part. The idea is the same. I'm going to try and subtract one equation from the other. So I'm just going to write this one underneath this one. So I look at the coefficients on my y's. A 2 is not a 1, so I don't have a match there. And a 5 is not a 4. I don't have a match there. So I need to scale one of these up, or maybe both of them up, in order to get a match on the front. Now, if you look at this one here, if I doubled this, I'd have 2y, and then I'd have a match. So I don't need to scale up the top one. I just need to scale up the bottom. If I did that, I'd have my top equation, right, 2y minus 5x equals 7. And I have 2y plus 8x equals 20 if I double this one. I'm free to eliminate now because I have a match. 2y's minus 2y's ends up giving me 0. Negative 5x minus 8x is negative 13x. And 7 subtract 20 is negative 13. So I've only got negative 13x equals negative 13 now. I just need to finish by dividing by negative 13. So my point of intersection happens when x equals 1. Once I have an x, I can put it up into a y. I could put it in this equation, I could put it in that equation, I could put it in this one. It doesn't matter, you just pick one. I'm going to choose this one because it has just y, not 2y. So it'll be easier to do. So y plus 4x equals 10. Put my x here. Y is 4 times 1. No, y plus 4 times 1 equals 10. So y plus 4 equals 10. Kick that 4 to the other side. 10 minus 4 is 6. So I have a point of intersection at 1, 6.